Okay, we meet again for the second video for the torsion topic. Okay, so now we continue the second part for the torsion. Okay, normally when we talk about the torsion, okay, we always refer to the strain displacement analysis, or normally in simple word, we want to see how this metal rod has been strained during the rotation. Okay, so this one you can read by your own, but I want to highlight in one very important rules. Okay, uh, in torsion, okay, normally they have something like we call a positive torque. Okay, what is the positive torque and what is the positive angle of rotation? Okay, normally for positive torque, okay, it's the moment that acts on the cross section and acts in the right hand rule sense about the outer normal to cross section. What is the positive angle of rotation? Rotation of cross section at x-axis in the right hand rule sense about the x-axis. Okay, this one is the positive torque, and another one is positive angle of rotation. Okay, so what is the positive angle? Okay, meaning that we follow the clockwise of the rotation. Okay, so normally in torque, okay, we want to know whether the sample face the contractions or expansion. Okay, normally for torque, uh, normally the metal experience the how I say the negative or the contraction of the metal when we apply the torsion mode. Okay, uh, as I mentioned earlier, okay, when we talk about the torsion, normally we refer as always as a strain. Okay, this one I show you torsion stress strain curve. Okay, when we talk about the stress strain curve, okay, at the beginning of my lecture regarding the tensile, you can see the y-axis refer to the stress, and then x-axis refer to the strain. But for torsion, when we apply the load, okay, meanings that uh, there's another graph we call as a torsion stress strain curve. Okay, as you can see, the pattern of the graph is similar what we have seen in the tensile test, except the y and x axis we refer as a shear stress and shear strain. Okay, what happened if the shear stress presence at the elastic region, and what happened if the torsion occur at the plastic region? Okay, uh, I want to give you one good tips. Okay, for torsion, you need to understand where and when to use the equation. Okay, in torsion, number first rule is that, as I mentioned earlier, it must relate with the angle. That's number one rules. Number two, the distance of the sample is required in order to allow torsion to happen. And then, of course, the radius uh, of the twisted angle is needed in order to allow the torsion. Okay, in this case, okay, this one the first equation related to the shear strain. Okay, normally for the shear strain, uh, we always refer something like the I can say gamma symbol. I'm not sure about the symbol, but normally we can use this kind of symbol. Okay, equal to the radius of the sample. Okay, and then multiply the angle of the rotation in radian, and then divide it by the length of the sample of the metal product. Okay, this one the formula for the shear strain. Okay, this one same as a previous slide, but as I mentioned, when we talk about the uh, you know when we talk about the shear strain, meaning that the calculation must be in radian mode. Okay, and then the shear strain actually is the proportional with the radius of the uh, rotation. Okay, normally this statement is really important. Okay, the shear strain, okay, is proportional with the radius of the rotation. Okay, this one I already explained in the video how this one rotate by applying the load at the edge of the road or the block or whatever, and then must be in opposition direction. Okay, okay, this one I want to share with you. Okay, I put the important notes here, meanings this derivation is really important. Okay, to be honest, I love to give a student a calculation based question. Okay, but I won't ask how to derive the equation. Okay, because it's beyond EBB 344 scope. Okay, but I will test you on how you apply the equation at certain conditions. So meaning that you need to understand the derivation of the basic equation for the shear strain here, as you can see here. Okay, and then it can be applied at different mode of the conditions. Okay, what I try to say here is that, okay, for example, okay, this one the shear strain maximum. Okay, normally sometimes in the question ask you, okay, the shear strain maximum is this. Okay, you should just use this one at this place. Okay, and then the C actually is same with the previous slide. Okay, it's because this one I take from the books, so meanings that actually P and C is same. Okay, in the previous slide, P is the radius. In this case, C also is a radius, and then theta is a angle, and then the length is the length of the samples. Okay, from this equation basic for the shear strain, you can derive it for different kind of mode application. Okay, for example, if you want to calculate the maximum shear strain of the metal rod, it's same like you use the normal shear strain equation. Okay, and then you can derive it, okay, until you get uh, this kind of equation. Okay, so please pay attention on this. Okay, because in the next video, the last part of the video, I will give you two exercises, okay, together with the answers, and then later you should do by your own. Okay, try to find how to get that answer, because the answer I already give to you, and then you need to calculate, you need to apply how to solve that questions. Okay, and then uh, as I mentioned earlier, okay, this slide, okay, I think here. Okay, the torque here, let's say in the elastic region, okay, the torque is equal to G multiple shear strain. What is the G means? Okay, G is referred to the Young modulus, shear Young modulus. Okay, normally for normal Young modulus, we always refer as a E. Okay, capital E. But for the shear, for the torsion, normally people always refer as a shear Young modulus, and then they always represent as a capital G, Ghana. Okay, and based on that equation that obtained from the elastic region, okay, they will come up with this equation. That's why when in elastic region, the Hooke law has been applied. Okay, has been applied. Okay, the torque equal to shear Young modulus multiplied by shear strain. Okay, meaning that, as I mentioned before, the radius is proportional with the the shear strain is the proportional to the radius of the sample when the torsion is applied. And then the formula for the torque is that torque equal to Young shear modulus multiple shear strain value. And then from this equation you can derive and combine with the previous equation that you have seen in the previous slide here. And then when you derive it until you get this kind of uh, equation. Okay, that's why actually in torsion there is a various mode of question that I can ask you related to the calculation questions, because from the basic equation of the torsion you can derive in different mode of the um, uh, formula. Okay, all right, so this one I think I already explained to you the difference. Let's say if let's say if we use the more brittle metal rod, okay, what happened to the fracture surface after tensile load has been after the torsion has been applied on the material, or the metal rod. In the case of the brittle metal, you can see the fracture surface looks like flat surface, but meanwhile if you choose to use the more ductile metal rod, after you exceed the torsion maximum load, and then it breaks into two, you can see something like the the fracture surface something like in the rotation mode, as you can see in the figure 4.177b. Okay, and then okay, for the angle of twist, this one the derivation of the again combination between the shear strain equation as well the torsion at the hook law condition. Okay, from this derive, okay, and then you can get this kind of equation. Okay, so what is the J? What is the G? Okay, this one shear strain max equal to torque max divided by Young shear modulus. Okay, since that the TC max is the TC over J. Okay, you need to understand, okay, what is the T and C and J means. Okay, T max is the maximum torsion, and T is the torsion that's been applied, and then C is the radius, and then J is what? Okay, you need to think, you need to find out J refer to what. Okay, normally J refer to the volume of the metal rod. So it means that, let's say if you have a metal rod, the formula for the volume is different when you compare using the block shape uh, metal for the torsion application. Okay, so please pay attention on this equation. Okay, please open some references. I think you can open the HB, I think HB books, okay, in order to look out. Even you can go to the Callister book to see example how to apply this kind of equation, especially for angle of twist in the elastic range. Okay, again, another way to explain the torsion is that we need to this one the power. Okay, okay, when this power equation will be used. Okay, of course, as I give you example earlier, in car, okay, the drive shaft of the car has been installed near to the tire, so meaning that this shaft will help the tire to rotate. Okay, when this tire is rotate, that's why the power is generated. Okay, where you can see this power has been generated, okay, when you see your meter in RPM, right, rotation per minute. Okay, that's why we can say as a power. That's why uh, let's say you can know, okay, this one, let's say 1000 rpm. So meaning that okay, you use high power for your drive shaft. That's why when you drive a car, when you drive so fast, for example 160 or 180, you will be capitalize the maximum intensity of power for your drive shaft. That's why when you always drive fast, that's why that will shorten the lifespan of your drive shaft. Okay, come back to this equation. This equation explain to you how you derive from the basic equation in order to calculate the power for the transmission shaft. P equal to T, W is the angular velocity, or equal to 2 pi F, and then F refer to frequency. Frequency is 1 over T. So meaning that there is many ways how to ask the question regarding the power of the transmission shaft, particularly for the drive shaft for the car. And then this T is referred to the top, uh, equal to power over 2 pi F. Okay, this table shows you, I summarize a few, not few, I think quite numbers of the equation that popular use in the torsion calculation. Okay, so you can go through this as well, you can check in the books. Okay, I think that's all for the second part of the video. I think my explanation is quite long for this particular explanation, but believe me, when you do the next exercise, okay, for the third video, I will explain to you how you need to do the exercise. Okay, I just give you two simple, not simple, it's quite difficult, but that's why I give you the answers and then I give you time to solve the question. So therefore, you can experience by your own how the question has been used in order to solve the question. Okay, please stay tuned with my last video later for the torsion part. Okay, thank you. See you then.